I'll talk about instruments for this energy range, a roadmap to gamma ray astronomy, and a mission which I call here tentatively dual, and its relevance for gamma ray burst science. Now, is there science beyond gamma ray bursts in this energy range? Just to remind you that, of course, there is people who are interested in nuclear lines, either by excitation, radioactivity. Lots of, the same breakthrough which happened in the 19th century when Fraunhofer first discovered, and then Kirchhoff and Bunsen had actually understood the atomic lines. Remember what they did to astronomy. It became astrophysics. At one point, we want to do this for the nucleus. Then, of course, there is all these thermal, non-thermal transitions of the cosmic accelerators. Here, compact objects in the galaxy, often accretion, ejection schemes which look a little bit like gamma ray bursts in a certain way, also extragalactic sources. And then, of course, other enigmatic features like the annihilation of here electrons and positrons, but of course, in the end, that's not all. That is all also part of gamma rays beyond bursts. Now, I'm not going to talk about the science. I'm going to talk about the common instrument. Now, let's look at instruments in astronomy and in this quite impossible region here. Here you have all the instruments we know, Earth and spaceborne instruments. Here up to UV, you can make total external reflection. And basically, all instruments look the same. It's whatever, a reflector. You concentrate on a small position-sensitive device and make an image, direct imaging. And above a certain energy, when photons really behave like little bullets, you again can just do it by tracking detectors. And then there is this impossible range where you're kind of in a transition zone here where they're not yet really doing very nice tracking features and where they not easily be reflected anymore. And that's where many astrophysical sources actually have their emission maximum. This is where AGNs have their maximum. That's where many gamma ray bursts go through their maximum. And that's where you find a lot of interesting features like radioactivity, excitation, annihilation. So it's an extremely interesting range, but it's kind of impossible.
Is the maximum because that's where the cross-section is the lowest, or is that because the processes concentrate? Is that because of the temperatures, or it's a combination?
There is all of that. Of course, there is reasons to the rich physics. It's a transition region, so you lap in also with the emission physics from both ends. Now we talk a little bit about that. Up to now, we had a real brutal approach. We just did shadow casting in different ways. We somehow, in a certain general way, we call it modulating aperture system. It's just Euclid. Light goes on straight lines. So you put a lot of matter somewhere and you let it go through holes, and you hope to kind of modulate the signal either temporally or spatially. Temporally by just having kind of a bucket which you point to the source, point away from the source with heavy walls. This has been, for example, the case for the OSSI instrument here on GRO. It's just 4 big collimated light buckets. You go on and off. Of course, you have always 2 on, 2 off. And you see a slight modulation. Signal is always extremely weak with respect to the background. We're here not talking about the gamma ray bursts. Talk about that in a minute. So this is one way to do it. Another way you know well from the BATSI instrument, which of course did this map here you talked about this morning, this uniform distribution of gamma ray bursts, but it also made a funny new way of doing images. You buzz around the Earth, and the Earth becomes kind of an anti-collimator if you look down from Cygnus X1 down to the Earth, you would probably see it this way if you can zoom in. And so the detector disappears behind the Earth. So you have a cutting edge where you lose the signal from Cygnus X1, and 45 minutes later, whoop, Cygnus X1 rises and you have an edge. And on these edges, you make a sky map as the orbit kind of makes its precession around its mean orbit. So this is a second way, and then is of course one everybody now knows sufficiently, the coded mask. You don't use a temporal modulation. You need a little bit a more complicated position-sensitive detector, and you project actually shadows, which you pick up with a two-dimensional detector. This is the sky map, for example, we did on the electron-positron annihilation here in our lab. It's the latest map where is this slight asymmetry, which kind of disturbs people who would like to see dark matter signature in these decaying light dark matter particles, light neutralinos. So we could, of course, speak a long time about that. That is done by the still operating integral SPI telescope, which is based on this. Okay, so this is basically the state of the art in a nutshell, very quick. One could, of course, have a whole week of lectures about what we did. Now, this is kind of where we came from. You have time and energy coverage in a kind of a roadmap. And you see the golden ages during GRO in the 90s. You see that we are again in a golden age right now with Newton, Chandra-Nix. We have Integral, Swift, Agile, and Fermi all operating. So it's quite good. New star will come up here now. But as you see, there is a hole here in the future in the MEV band. And this hole, if you make the line here, if you go to the red line where we stand today and you unfold it and look at it in sensitivity terms, you see that in Fermi we are extremely sensitive. COMTEL is actually the instrument which was best in the real MEV, 10 MEV range, and we have been working here in the hundreds of keV range with SPI and DISCRET, but there is a tremendous hole. It's not only something missing in the future, it's already missing there just to bridge the gap between X-rays and high-energy gamma rays. This thing here, which we miss, is something like at least a factor of 30 in this energy range. Somehow, we have been held back here. If you look at the same map here for one enigmatic gamma ray line, 847 keV, that's the nuclear decay cobalt, nickel to iron in supernova. People would like to understand how supernova produce elements, all the stuff which is around you and yourselves. And also, since supernovas are these cosmic lighthouses, you would at one point like to understand them. Of course, you know that that's something really apparent of your gamma, of your hypernova, of your gamma ray bursts. So one would like to not only hear, as we have become factor of 7 or so better over 3 generations of instruments, we would like to become now, in one decade, something like a factor of 30 to 100 times better. But why hasn't it happened? Why did it not happen before? So this is a gamma ray catalog. You see X-rays on the left, high-energy gamma rays on the right. Up to now, there is the gamma ray catalog is, of course, enhanced by a factor of 10, probably, but the general structure has been the same. So in the MEV range, we have a hole. There is such very, very few sources. Even if you put the new sources from Chandra, SPI, IBIS, and Fermi in there, we have a hole. Why? Did the good Lord make less sources there? Or is it just that, say, we go through an interaction minimum here in the MEV range, photoelectric effect comes down, pair production is not yet there, and you have kind of a bridge in the MEV range. And then, to make it even more fun, you have an absolute maximum of wonderful background physics just about there. All the activation of all the passive matter on Earth and in the sky in your spacecraft will just get hot from cosmic rays, which convert into neutrons. Neutrons produced by capture radioactivity. And you have all these wonderful gamma ray lines, but they're in the background. So there is lots of incredible physics, but it's just kind of impossible to do something there. And now they ask us to jump from, a few times 10 to the minus 5 photons per square centimeter in second. That's the sensitivity we have. We should now become better. Theorists tell us we have to jump by a factor of 30 or 100 to 5 times 10 to the minus 7 photons, square centimeters in second. You must be out of your mind. This means detecting 1 photon per square centimeter a month. Knowing that the cosmic rays bombard you by 1 cosmic ray per second and square centimeter, and producing, say, at 511 every minute a photon in a germanium detector. So it seems to be completely impossible. So if you would like to become 30 times better, it's not. This is the integral speed detector here with its coded mask. It's a ton-type instrument. So if you want to be 30 times more sensitive, it's not 30 of these things. It goes with the square root, as you know. It's 900 speeds to become 30 times bigger. So it's something of kilotons, which you would have to pull into space. So this is something which seems slightly improbable right now with the common situation. Another thing is that we have the sensitivity to reach 30 times better doesn't seem very likely with the present generation. On the other hand, we need to cover an extreme band of angular extents. We know that we have to go to supernovas, which are, of course, far in the subarc second range. We would like to look at microquasar jets, which are in the minute range, at small supernovas in our galaxies, remnants, supernova remnants, which go now from the minute into the degree range till, say, the 511, the positron-electron annihilation, which is something which is 8 or so degrees in the galactic center. It's big as a fist in the galactic center, and we cannot resolve it yet. So the sensitivities you need are here lined out on the left. So somehow it's very schizophrenic. At one point we would like to go to see these guys here on the lower left and still say something about the big diffuse things on the upper right. Somehow we have to attack it on all fronts. Seems completely impossible. Now, let me talk about some hobby I have done to attack the guys on the lower left. Here is the 3 principles of gamma ray detectors. Actually, they reflect the 3 ways we look at light itself as a geometric property of a beam going in straight lines. Here on the left, geometric optics, Euclid, quantum optics, Newton if you like so, little bullets, and then wave optics to the right. So we will first talk about wave optics, which is something which up to now has been declared absolutely impossible, since the wavelength of gamma rays are 100 or 1,000 times smaller than the distance between atoms in solids. Well, this is kind of true, unless you kind of arrange your matter in a particular way. You take Bragg crystals, here it's copper crystals, where atoms are aligned like soldiers in Prussia. And so if you look between these alleys of atoms, you can see walls. And under the condition that there is an entire number of wavelengths between the incoming tracks here, you can actually diffract gamma ray light on these crystalline planes. So under the red condition up there, which is a Bragg condition, you can deviate in a coherent manner gamma rays by, say, a degree. Now this is, of course, you would not only do it in one of these little, say, 1 by 1 by 3 millimeter sized copper crystals. You would then put them on a ring, and all of these crystals would then focus on one point. You take another crystalline plane, another Miller index, here is the 111, you would take the 100, the 200, and so on, and build a lens where everybody basically focuses the same energy. So we have done this first in the lab, and well, I jumped right away to the balloon flight we did with this thing, which was called Claire.
How long is that?
2.70 meters focal length.
But the lens is much bigger.
The lens is 45 centimeters, 600 little crystals.
So you're needing a lot more than 1 degree.
Here we are doing hard X-rays. We're not doing 511. We're doing actually 170 keV, where 511 is the third harmonic. So we only wanted to test the principle. We went to hard X-rays, 170 keV, and look at the Crab Nebula, which doesn't have a line there. So we looked at a piece of continuum, which is kind of absurd, because, I mean, if you have this Bragg condition, you only see in a small wavelength band. But we needed to test it. People told us, if you don't see an astrophysical source, they never buy it. So we did it. Well, first we tried it out in the lab, just to give you an idea. This is our lab setup here with an optical bench, 14 meters. We did it at the energy of cobalt-57 radioactive line, which we could also do in the field. Then we went out behind in the night to the parking lot when people were gone, had a 36-meter bench, illegal, and beamed our X-ray generator out in the parking lot. Still worked. We then also did it on an airfield, and in the end, on 200 meters, and in the end we tried it out here on a balloon flight in 2001 here through France. And the grad student here, Hubert Allouin, who needed a year here to get the whole orientation right, because we had to point under a balloon to 3 arc seconds, which is not an easy thing for a small team. But we did it. And once he figured it all out, we had here some 33 photons. He knew the first name and the name of his guinea pig of every photon. So he really knew it by the end. So we figured it out, and we showed that you can do it. Here above you have the distance and with respect to the energy. And we did it at 170 keV on the 33 photons of the Crab. We also did it on an airfield here on 200 meters. So we consider that we have now demonstrated at least a principle even on an astrophysical source. We have continued developing crystals. I'm going over this very quick because it's really very far from gamma ray bursts. It is actually not for hypernova. It's more staring at supernovae and looking at their radioactivity. And so we are now at unbelievable efficiencies for certain very exotic crystals, which we look at one by one at the synchrotron radiation source in Grenoble. And we are now in quasi-mosaic crystals, which are even better than what I now have here. So we are constantly evolving and now have lenses which go up to efficiencies of 60%. This is quite astonishing.
Quasi-mosaic work? I mean, are you essentially lining them the way they would in a circle? Or are you just putting these crystals together and compressing them?
No. Yeah,
that would work.
Oh, it's a very good question. Actually, it's a Russian invention from the 50s. The word is not really adequate, but it has been kind of become the word of this. You take a perfect crystal, a germanium crystal or a silicon crystal is even easier. Must be perfect. You slice it, and as you slice it, as on the barbecue, your steak, if you slice it on one side, it curves. And it curves actually in one direction. This opens your rocking curve and gives you an energy band pass, and actually also doubles the efficiency. And then it curves in a second. This is the secondary radius, which refocuses the photons, which otherwise would fan out. So you have two gains, one in with respect to mosaic crystals, where you only can maximally have 50% of all the photons diffracting in your direction. Yeah, I'm a little bit too quick. If you come into a normal crystal and you have little crystallites, the beam goes back and forth, and it comes out, it's basically 50-50, minus the absorption. Say absorption takes away 30%, so you have, say, 35% in the direct beam and in the refracted beam. So you cannot theoretically do more than, say, 30%. Now these gradient crystals do already double of it, because you curve it, so a photon going in has never the chance to go a second time in the same Bragg angle, and will just diffract once, and that's it. And these quasi-mosaic things, they're twice curved, and they even refocus. So the focal spot becomes even smaller. So okay, I'm spending too much time on this. What we did, we showed it on a balloon. We have done an R&D for the French Space Agency, where they have shown that it can be done even in a formation flying configuration. And then we have raised some 200 scientists which signed up for a cosmic vision study of ESA. Unfortunately, we didn't win, and that's where we are still on our way. Now, okay, you will say that's fun, that's all that stuff here, point sources, gamma ray bursts, who cares? I mean, what about gamma ray bursts? What is gamma ray astronomy thinking about next detectors? And you have heard it this morning here, that we think of Compton telescope as wide field telescopes. So the principle, I go over this rapidly, is to make a rebound, a ricochet, measure two positions, two energies, get out a scatter angle from the Compton scatter formula, and many teams now are on the way. You have from Toru Tanimori this morning heard about his time projection chambers. There is actually a Columbia Rice group who tried that in the late 90s. Elena Aprile, Uwe Oberlack, and so on have actually done this. Now we have the Kyoto University et al. Who tries it in a different way. We hope, of course, that all this will work out. There is now, since 2 years, a very promising balloon flight from Rice University, which has done it with double-sided strip detectors, silicon strips, sodium iodide and cesium iodide calorimeters around. The data under analysis, I think they haven't yet seen the crab. And there is a third, well, actually it's the first one, which has now worked. It's a germanium double-sided strip detector instrument from UC Berkeley and allies. We are part of this. Now, okay, that's what is done for new wide field instruments, but this has started much earlier. You remember, I showed you this morning, we have had COMTEL, which did this first all-sky map in a radioactive nuclei, aluminum-26. We have the Munich group, which has then shown that you can actually do polarization. This is data from an accelerator. And then we have shown here with UC Berkeley that you can fly these double-sided strip detectors 3D localized to a cubic millimeter the interactions. With also kind of a time projection, you use also the depth of the charge collection. And we have seen the crab here in 2009. Now, okay, this is potentially a very nice thing for you because it can do very wide fields. Look at it like this. Do they really have so wide fields? Take a detection of a coincidence event. That's what you need. You ask for 2 events and 2 detectors. Okay? So suppose that you can even have the flight time, you know that it went this way. So the event, the scattered event came from there, but that's not where the photon came through. You calculate the scatter angle, and you get this phi or a phi bar from the 2 energy deposits. Okay, so it's really a wide field because not only you could come here from the upper left, you could come from here, and that makes you kind of a 2p field of view. That's actually true. But what is even more true, and that's the hic, the problem, that you can also come from here. That's the same event you project in the sky. And it is so much more likely that you come from this bright atmosphere that it is absolutely unpractical to accept those events which allow you to come from the atmosphere. What you do, you must restrict. Scatter angle and scatter direction must do that you just cannot come out of the atmosphere. So this way, you get a much more reduced field of view for lower Earth orbit instruments. It's more likely 2 or 3 steradian and not 2 pi steradian. So there is a factor of 3 or 4 or so between what you think you can get and what you then actually get. And to this, you can imagine this is a very bright gamma ray source. It's the brightest source we have. Actually, we have seen it this morning. On the left, calibration data from Comtel, on the upper left. Go ahead.
You have to shield from upward going, basically.
We are about to talk about that. Say your...
Is it possible with passive shielding, or does it have to be active shielding?
Has to be active shielding. But we'll talk about this in a sec. So this is Comtel. Comtel did only have plastic shields, very thin, very lightweight, because it had a time of flight. There was 1.50 meters between the 2 detectors. The detectors are very fast, scintillators, so you can tag and measure the timing. You can see if it's backwards or forward. It's about 3 nanoseconds between the two, between back and forth. 5 nanoseconds each way. So there is a time of flight, channel number 100 in the accelerator in Neu-Herberg. It was very easy. Once you hold the telescope upside down, once the other way around, and you see the 2 ways of photons going through that instrument. The bad ones are red, the green one, excuse me, it's a very old illusion. Here, yeah, shouldn't say that here. It's not good taste. But okay, it's like at the red light. You don't want these. You don't have the green ones. They come from above. They go downwards. Now in flight, we have seen this graph here also rapidly this morning. It looks very different. If you would cut at channel 100, you're dead. You have to make a very small time of flight window. And here you imagine the whole dump which comes from below, from the spacecraft and the Earth. Look how much there is. You hardly don't see the signal at all. Well, it's not even signal, it's just stuff which comes from above. Actually, most of that is again background. But in there is somewhere a part of the signal here. So it's ridiculously small. So there's different ways now to cope with this. Comtel, as I said, did it with time of flight. So that means...
Peter, some additional selections were also... Yeah.
Of course, you get out the neutron from PSD and so on. There is lots of other little tricks and energy selections and so on. In the end, it's quite complex. So you have here a common telescope where you would like to have a high efficiency by pushing the 2 detectors close. That makes a big field of view, and that makes sure that you go from the upper detector to the lower. The problem is that this, for modern telescopes, as I just shown you, it's only centimeters. And the time of flight is just not practicable. If you have, say, 10 centimeters, you're in the sub-nanosecond range, you cannot tag, particularly not if it's semiconductors, you forget it. So you must bring them apart. And that costs, because now not everybody can come in anymore. The other green line here just drops out. So it needs long baselines, low probability for coincidence, and low efficiencies. This huge ton, more than a ton, like Comtel, had a few square centimeters in the end. So it's percents, 2% or so, depending energy, of efficiency. Few square centimeters. It's ridiculously small. Now, what you can do is you say, okay, let's push these things closer together, make it more compact. As all these mission studies here do, ACT, GRIPS, CAPSIT, they make more compact sized instruments, which gets much higher efficiency. You can go up to, say, 10%. And in principle, with quite some mass here, 1 to 2 tons, you should get the sensitivities which are indicated here. Field of view of 1 to 2 steradian and a modest angular resolution of a couple of degrees. We talk about this later. The trade-off here, why are these things so heavy, is because now, since you cannot measure the upward going guys, here you're right, we need a shield, and it must be active. Otherwise, it even creates more background. It would probably not matter so much because you're already 2 pi is just matter, spacecraft and Earth. But if you want to get away with part of that, you have to make an active shield. And these active shields are usually of the same order of mass than the instrument itself or more. In integral, say, SPI was 16 kilograms of detector and 600 kilograms of anti-coincidence, just to show you the waste. Beside of that, the shield is never really tight. Shield is as tight as you can do it technically, so it's not really tight, and it produces lots of neutrons. Neutrons activate radioactively clear instruments. So it's not a very good thing. They're often more massive. They cost lots of your instrument weight. So what is the next option? What I propose here, this dual option, is basically just to not go where the background is. That means get away. Get away in L2 and logically put your spacecraft away from the detector, which has another trade-off, which has another win. You see now that all of a sudden you not only get 1 steradian or 2, you get 4 pi steradian here. So this is like having an instrument which is 4 to 6 times larger. So you can afford to make a small detector, and the time is paying off. So the idea is just to get away from the background to L2 and on a mast. Doesn't look so evident right now, but I will show you why. So it looks like this. Detector sits here very well away from the mass. And you see the whole sky. We know that this works. It reduces background tremendously. Some of you remember Apollo 15, Apollo 16, in their trans-Earth coast between Earth and Moon, they deployed kind of like a tape ruler with a little a little sodium iodide detector on the end, 7 meters long, and the background here dropped by a factor of 10. You see the 511 line, it's an order of magnitude. Just solid angle effect. Just get away from where the background is on the spacecraft. And it was just a simple tape ruler type, double tape ruler type of thing which brought the detector away and made the solid angle collapse, and you win terrifically. Now masts are not something so antique. It's true they did it at the time, and ever since, people who did planetology used masts, whereas we, the astronomers, used shields. Now, if you're militaries, guys here, you know that there is 2 ways to get away without being wounded on the crossfire. Either you build kind of entrench yourself, fortify with sandbags, or get away from the fire. Now, these guys in planetology, they always preferred to just get on a boom, because they study things which get activated by cosmic rays, like Mars and Moon and so. So they knew that the material which is bombarded is hot. So they wanted to get away from their hot spacecraft. We always did it the other way. We said, let's build a wall. Now, meanwhile, planetologists built some shields, and I think we should get to have some masts. Actually, it's not an antique. In probably less than 5 hours now, you have another mast in space launched by a Pegasus by the end of the session. Right now, they said 4 hours when I looked before my speech. If you like, you have all the web here. You put that website and you are live broadcast on the launch, the Pegasus launch. It's a 10-meter mast. There is here refractive multi-layer optics, cadmium telluride detectors on the focal plane. It's quite sophisticated instrument. It's only 360 kilograms and launched by basically an airplane. Now we would like to do something a little similar, but put at the end of the mast not the mirrors, but a small detector. It could resemble to this one. It could resemble to Taurus 1. Here, just as a sample, we multiplied our balloon instrument, the NCT, Nuclear Compton Telescope, to what we call the all-sky Compton imager, the ASCII. It's basically the same instrument, we just have a higher, probably 6-7 times bigger surface. And since we stick it on a boom, on a fishing rod, it can work probably the first time in astronomy from above and below. It just sees the whole sky at once. We simulated this with megalib. Here you have the angle here of incidence from zenith to nadir, going all around. Of course, there's a little bit more matter here from the size, so it's not completely homogeneous, but this is basically what this thing would do. And it would probably be the first detector which sees the whole sky every moment of its mission. And you now understand the interest for gamma ray bursts. The angle resolution is not terrific. It goes from 1.5, say, to 2.5 degrees. Narrow line sensitivities, now we can say over the mission lifetime, because every source in the sky will have an exposure which corresponds just to the mission lifetime. We don't have to point. This thing points all the time, all the sources. So if you mean this out, this angular response, you get some 10 to the minus 6 up to down 7 times to the minus 7. So this is about the objective we want. But okay, it's only working for constant DC sources, which are just there, like radioactivity, like annihilation. And for short flashes, of course, it's a little different, although they're, of course, measured. We talk about that in a sec, about the polarization sensitivity also. But okay, what do we do about supernova, which only go off for a couple of weeks, and then are probably still there for a month or two? So we have this dual thing, which is an all sky monitor all the time. The idea to get sensitivity is that sensitivity is made by surface and time. Time has no mass, so it's a really small instrument. And the fact that you see everything all the time gives it the sensitivity. And you take this here to focus a beam from a gamma ray lens. Now this is here becoming a dual instrument. This thing does nothing about everything, and this thing here does everything about nothing. So it's going very deep in, it's a very small phase space, but there it goes all the way down, right in 10 to the 6 seconds, that's the job. Whereas you need for the all-sky imager 3 years to sum up. So let's be quick talk about this Lauer lens. Here is the thing we...
How many supernova are there up to 14 megapascal? So is it enough or the lower line? No,
we would get the supernovas down with the sensitivity you will get. We talked about that in a second. I'll show you the sensitivity of the lens. This corresponds to about 40 megaparsecs. So this is the lens which would go there. You hardly see it. It's about 350 square centimeters at peak. So you can say it's 5,800 little crystals, all focusing on basically 1 square centimeters. It's a meter diameter, 80 kilograms with the substrate of cesic, focal length of 30 meters. So that means you collect about 300 square centimeters and focus them down to 1 square centimeter. So that's where you get about an amplification of a factor of 200, first time thing in gamma ray astronomy. It does it only in an energy range between 800 and 900 keV. You see the different crystals here spreading out to make this kind of Gaussian. It has a spectral resolution with it outstanding, which is the best you can get, better than 1% germanium resolution. It has a field of view of about 5 arc-minute, and in there, certain imaging of 1 arc-minute, and it goes down to a broad line sensitivity of about 2 times 10 to the minus 6 photons square centimeters in second. That's what you need to go to this distance. Here's what we think we get. So this is the narrow line sensitivity, and the broad line sensitivity is this cross there. And we would focus on supernova radioactivity of this thing.
How long is that boom?
How long have you to point?
The boom.
The boom, 30 meters. 30 meter in this case. I can show how you would do it.
And then the problem is you have to keep it stable. You have to keep it from tipping.
The thing is the Compton telescope is about 30 by 30 centimeters. And you just have to stay on it with the focal spot.
You just let it wander.
You can, as long as
The boom is vibrating a little.
the will, of course, vibrate.
Right.
Well, that's what they studied at Zinner. I can show you their solution.
You need to consider 2 booms.
Actually, they think of 3. They think of 3 booms. Yeah. They think of 3 booms. It's good. I go quick now. So here is this 847 gamma ray line. You see where we get in 10 days with these lenses. We get to the same place in 3 years with the all-sky monitor. The problem is it's not an extremely good imager. And so as an additional option, you could think of this. You could think of looking here at the annihilation map. This is about this 8-degree bulb here at the galactic center of 511. And of course, the event circles from the Compton telescope here, they would give you an angular resolution here, but it's not very good. It's 2 to 3 degrees at this energy. It's not very super. So one thing could be to help a little bit with another optical toy here from prehistory. Just put here beside of this lens here, which is on the upper part of the spacecraft, just put a lens, a coated mask there, and spend half of the time when there is no supernova to look at, just spend it on the galactic center, all on the galactic center. That means 1.5 years on the galactic center, which would then give you the sensitivity I just shown you, and which would help to do this to the 511 line. Here's the different 511 sensitivities of the different instruments over time, balloons, HEO, SMM, OSSI, SPI, and dual would bring it down here. So it would kind of make sense. Now what would it do for you guys? Here is the sensitivity calculated again by Megalib. Actually, it's not only Megalib, it's also Zoglauer himself. The guy, some say he has written the source code for the good Lord himself, for Klein Nishina. So he's the same guy who did the sensitivity for grips and capsid and so on. So don't ask me if this is how it is done. It is done by Zoglauer, like yours. So this is the fluences here. You would 6 sigma fluence in the 100 kV 10 MeV band for long and short bursts. We can also imagine a burst mode where you store the data on board and transmit them down later. And for polarization, here it gets you some, if it's 50% polarized, you have about 180 gamma ray bursts in the mission. If it's only 10%, probably 60 over the mission. This here is the modulation here, and as a function of flux, fluence at 100 keV. This is simulating a burst with a standard two power laws and a break here at 150 keV. So I think I can stop with this. reminding you that with this thing, not only we would go very deep for supernova with this Laue lens, we could resolve the 511 mission from the bulge, and we would, of course, at the same time do the job on many galactic center sources. And then the survey instruments can do all radioactivities, aluminum, iron, titanium, and so on. Do the annihilation line on the whole sky, now also, of course, and if there is extragalactic. Do all the compact sources, especially the ones which are far from the galactic center now, where there is no confusion like AGNs. And then, last but not least, of course, do gamma ray bursts, localize them, it's direct imaging. We would have much better than a degree here, since there is no background in a gamma ray burst. The localization would be perfect. Spectroscopy, again, spectacular, better than 1%, and polarization, as I just mentioned. And I think with that, I'm open for questions. Thanks.